All right, so let's take a look today at section 3.1, which is the beginning of polynomial functions and their graphs. All of this stuff should be reviewed for almost everybody, and if there's things that you come across that you're not familiar with, feel free to bring it up when I get back to school later in the week. So today, let's take a look, just starting out by looking at the vocab side of the polynomial functions here. So the basic idea, remember, behind a polynomial is just going to be a function that has whole number exponents. Whole number exponents. So this is what we think of as, a quadratic, a cubic function. The only things that are not going to end up being is when you have rational exponents where you have, say, raised to the 1/2 or raised to the 3/2. Or negative exponents, because that brings us into the rational function realm. Okay, so we're sticking just with polynomials. Okay, so another thing to know about polynomials is that when we're talking about their graphs of polynomials, their graphs are always going to be smooth and continuous. Right? So when I talk about them being smooth, that just means that they're not going to have any corners or what are called cusps, things like that. There's not going to be any breaks making it discontinuous, so it's always going to be continuous here. And breaks can be caused by a number of things: holes in the graph, vertical asymptotes. You can have, I'm trying to think what else you could have with that. Those are the main things, I guess. I guess those are two things that we've looked at. There might be others that I'm just overlooking right now, but that's the basic idea that we're looking at. It's smooth and continuous. Also, that means that you can draw the entire graph without lifting your pencil up from the paper. So drawing it in one continuous smooth curve. So when we're talking about polynomials, one of the things that the main piece that's going to define it is the end behavior, right? So the end behavior really is just the idea of just the idea of how the graph behaves as x goes to plus or minus infinity, right? We could say that that's an arrow right there. Then y goes to, and then whatever that behavior happens to be. Maybe it's going to be going towards a horizontal asymptote, maybe at y equals 0, or maybe it's going to positive infinity, maybe it's going to negative infinity. But the main thing here is that we're talking about the ends of the graph, right? There are a couple different things that control the end behavior. One of those things is going to be the sign of the leading coefficient. Okay, so the sign of the leading coefficient, EFF, there we go, make sure I can spell it. Okay, the sign of the leading coefficient. And we talk about that, that's just going to be, say we're looking at y equals to a times x raised to the b plus c times x raised to the d, and so on from there, right? So for this thing, the sign, the leading coefficient in this case being a right here, so if a is going to be greater than 0, so making it a positive number, right? We know that the end of the graph, we can say as x goes to infinity, we'd say that y will also go to infinity, right? Now, whether or not the graph is doing similar things with the left-hand side is a different story, and we'll talk about that in a second. But we're really just talking about the right-hand side of the graph. How does it finish as x gets bigger in the positive direction? If a is going to be less than 0, so making it a negative number, what this means is that as x goes to infinity, sorry, my mistake, to negative infinity, that y is going to end up being sorry, my mistake with that, sorry. I'm thinking about both ends right here. We're just talking about the right-hand side. As x goes to positive infinity, that y will then go to negative infinity. Okay, it has to either do one of those two things. I mentioned a second ago about horizontal asymptotes, but that's going to be reserved for rational functions. So here, polynomials in general, a is going to be a positive number, that leading coefficient. As x gets bigger, y is going to get bigger. And if it's a negative number, as x gets bigger in the positive direction, then y is going to be going to negative infinity. Right, so those are pretty straightforward. Right, the degree of the function is the other piece that helps talk about or address how things are going to be, how the graph is going to behave on the other end of the graph. Okay, whether it matches what the right-hand side is doing or it does the opposite. Right, so the degree of the function, remember, is the highest power of your variable, usually x, but not always. If it is an even degree, right? So 2, 4, 6, ... right there. That just means that both ends finish in the same direction. Okay, I'll put examples up of both these scenarios here. If it's going to be odd, okay, so the degree is going to be odd, so an odd number, 3, 5, so on from there. That means that the ends finish, I guess is a good way to write that, finish in opposite directions. I'm just going to abbreviate the opposite directions. Okay, so if we're talking about an even degreed polynomial, right? So even degreed polynomial, it'll look something like this. If the we'll say if a is going to be greater than 0, one end of the graph is going to be going up. The other end, because it's an even function, will be doing the same thing. What they're doing in the middle, I don't really know. It depends on the function, right? For that same scenario, if it's a even function, if a is going to be less than 0, then both ends will be going in the same direction. Okay, so that's going to be for an even function. If we're talking about an odd function, let's do a different color here. So let's say that if we have an odd degree function there, degree, we know that if a is going to be greater than 0, we're going to end up with the right-hand side going to positive infinity, and the left-hand side will be going to negative infinity, right? Once again, what happens in the middle depends on the function, right? If an odd degree function where a is going to be less than 0, they're going the opposite direction. So if the right-hand side is going to negative infinity, then the left-hand side is going to positive infinity, right? So when we talk about, when we describe the end behavior, we'll go ahead and use, we'll start to use the symbols that I put up earlier. So for this graph up here, we can say that as x goes to infinity, y goes to infinity, right? For the left-hand side, as x goes to negative infinity, y goes to positive infinity, right? They're matching up here. Same kind of deal here. As x goes to negative infinity, that means that y goes to negative infinity. For the right-hand side, as x goes to infinity, then y goes to negative infinity also, right? And then for these things over here, it's the same scenario, but since they're an odd degree, we know that as x goes to negative infinity, y also goes to negative infinity for that left-hand side. As x goes to positive infinity, then y goes to positive infinity here. Okay? And then we can fill in this last one here. As x goes to negative infinity, then y goes to positive infinity. Same kind of deal over here. As x goes to positive infinity, then y goes to negative infinity. Okay, there we go. Okay, so that's what we're talking about for the end behavior of these things here. All right, so when we're taking a look at these things, I think we've learned these kind of as rules before in other classes, but I think it's worth talking about, like, what does it mean? Like, why do we have that rule hold place here, right? So, I mean, if you're taking a look at something, let's look at a polynomial. Let's say that we have f of x equals to 4x to the fourth, and we have another one, we'll say g of x, which is equal to 4x to the fourth, so same leading coefficient, but then it has extra terms attached to it, so something like this. Okay. When we're talking about looking at this kind of setup here, we're looking at, I mean, we know this function right here, based on our rules, it's even degree, so both ends are in the same direction, the leading coefficient is positive, so both of them ends are going to be pointing towards positive infinity, right? As we're looking at the second one here, one of the ways to take a look at this is, since we're talking about as x goes to infinity or negative infinity, plugging in infinity or negative infinity doesn't really make sense, right? I'm just going to get, like, into g of x, I'm going to get, infinity minus infinity plus 3. Like, what does that actually mean? Is that just 3? Did the infinities cancel? Kind of weird to have it set up that way. So one of the things that I can do here is, if I factor out a 4x to the 4 from all terms here, right? What I'm going to be left with is 1 minus 7 over 4x squared plus 3 over 4x cubed to the fourth. 4x to the fourth, okay? And so remember, as x gets bigger and bigger, right, we're going to plug in bigger and bigger values into the fractions within this piece right here, which, if you think about it, if a larger and larger number is being put in those denominators, what happens to the overall value of the fraction, right? it's going to be going, at least the fraction pieces right there are going to go to a value of 0, right? Because the numerator is a constant, but the denominator is getting bigger and bigger, so the value of the fraction is going to 0. So really what happens here is that I'm left with just 4x to the 4th in terms of long-term behavior, which now if I go ahead and plug infinity into that, I'm going to end up with infinity, right? Infinity to the 4th times 4 is still just infinity, right? So that just confirms what we already knew previously, right? So we don't have to go through that, but that's the reasoning why that's going to work here. All right, so the next piece that we're looking at here is the concept of the intermediate value theorem. Okay, so it sounds really complicated, but this is called the intermediate value theorem. Excuse my handwriting. You're probably used to trying to decipher that. Abbreviated the IVT. Okay? All this says, like, if you think about this, super simple concept. If you're getting on the highway and you're accelerating to get onto the highway, if you make it to 65 miles per hour, right, at some point during your acceleration, you had to hit every single mile per hour between your starting speed and that 65 miles per hour, right? There's no jumping, right? I don't care how fast your car is, you don't jump in between 60 and 65 miles per hour. Like, you're going to have to hit all those numbers. You might do it really fast or really slow, but you're still going to hit all of them, right? So in something like that, my graph could look potentially something like, maybe I'm already going at a speed here, so it might look something like this, right? So I'm increasing as we go here. It's a little shaky there, but that's the basic idea. So what we're saying here is that if you reach 65 miles per hour, at some point in between when you started getting on the highway and when you actually got to your cruising speed of 65, you had to have hit some value in between here, which we'll call, B, whatever B happens to be here. And this would just be like f of b right here. We'd have to hit some value of b that's going to yield that speed, right? So at some point, at some time during there, we hit that velocity, whatever that happened to be there. Okay. And really, what has to have happened here is that you had to hit that at least one time. Could have slowed down because somebody was blocking you from getting on the highway, whatever happens to be. Eventually, you'll hit all of them at least once, right? So what this actually says is that if this is a polynomial, and you have two values, right? In this case, it was that 65 miles per hour. I'll call this A, and this was the 65 here. At some point in the interval from B to A right here, you had to have gone something in between those, right? So like maybe there's some value C in between here, such that f of C is going to be in between those, right? So I'm never going to put this on a test, but I think it's worth looking at what the intermediate value theorem actually says, and it says that if P, where this is going to be, call this like P of X here. If P is a polynomial, which it would be for this scenario, and P of A and P of B are, have opposite, actually have the scenario where, in this case, P of A is greater than P of B, right? Then there must exist at least one value, we'll call it C, where C is going to be in between B and A. I had them kind of switched around here, but I'm trying to hear that. Where A, so it's in between there, such that P of B is going to be less than P of C, which is less than P of A. And that's according to my graph that I have over there on the left-hand side. So this is going to tell, this is the intermediate value theorem. The book uses also to talk about the intermediate zeros theorem, which all that says is that if P of A and P of B have different signs, they have different y values. So it looks something like this, where you have some kind of graph here, like this, where A is, or this is B, I guess I called it before, and this is A over here. If it's smooth and continuous, because it's a polynomial, that means there has to be some value of C that has a y value of zeros. There has to be a zero in between there. Okay? And that actually goes with the last topic here, which is that there's a rule that we can say that for every polynomial has at most n minus 1 turning points